It's really important to know how to measure the energy of a wave because the wave didn't come from nowhere. The energy of the wave tells you about the energy of the thing that created the wave. For example, astronomers can look for gravity waves from black holes merging and figure out the mass of the black holes, the energy that they have. So we want to do that with our waves on a string. Figure out how much energy there is on the string and how much energy is required to generate the wave. Here in the animation, there's this red oscillator that generates the wave. What I want you to look at carefully is, as the oscillator goes up and down, isn't it stretching the string slightly? Look how the black dots are stretched out as the wave goes up and down. Also notice that, in other words, they're stretching, therefore there's potential energy involved in a wave on a string. Also, of course, the string is moving up and down as well, and the up and down motion indicates that there's kinetic energy in this wave also. So what we want to do is figure out the total energy involved, and that's going to be including kinetic energy and potential energy. Now, I'm not going to try to, I don't care about the total energy of the entire length of the string. What I really care about is just the energy density. In other words, how many joules there are per centimeter of the string. So we're going to be looking at energy density, and it's going to include kinetic energy density and potential energy density. So let's start with the kinetic energy first. We're talking about a sinusoidal wave. It's a sinusoidal wave, so we have y is equal to a, let's say it's cos kx minus omega t, a right moving wave. Okay, so I'm going to look at first the kinetic energy density. Joules per meter of kinetic energy. Kinetic energy we know is 1/2 mv squared. But in this case, not m, that would be like the whole mass of the string. It would be the mass per meter. In other words, mu, not m. So the kinetic energy density will be simply 1/2 mu times v squared, meaning vy squared. The string moves in the y direction, not in the x direction. So I have to plug in vy and square it. Vy is the derivative of y with respect to time, and it pulls out our factor of omega, like we've seen before. So I get 1/2 mu times omega squared from squaring the speed times a squared times sine squared. Sine squared of kx minus omega t. So that's pretty cool. That shows us that there's a wave of kinetic energy that travels down the string. It is a wave. It's of the form of a wave. It's sine squared instead of sine. But look at the animation. We can see that. Look how there's a place where the string is moving quickly up and down, and that travels to the right, and that's the kinetic energy wave that's traveling along. Of course, that's only half the story. We also have to look at the potential energy. Potential energy is a little bit trickier because it involves the stretching of the string. So I need to look at the stretch that's involved. The string definitely stretches. You see, if there's no wave on it, then what I'll do is look a little portion of the string whose length is dx. And when the wave is there, it's angled and stretched out. So between these same 2 points on the x-axis, if the wave is present, the string has some angle there, and it's stretched out like that, elongated. It's the same string, just stretched out up and down to be angled. Okay, so what I care about is how much the length of the string has changed. The change in length. The change in length is equal to the length when it's stretched, which is the square root of dx squared plus dy squared. That's the new length, the hypotenuse here, compared to the old length, which was just dx, how long it was originally along the x-axis. There's a reason I did the binomial approximation. This is screaming at us to use the binomial approximation to simplify the change in length. So this is approximately, I'll let you work it out using the binomial approximation. It comes out to be 1/2 dy over dx squared times dx. That's using the binomial approximation. Okay, so that's the change in length of the string, like as the wave goes by, now the string has an angle to it. Notice this is the partial derivative of y with respect to x squared. It's not the second derivative, it's just the first derivative, but squared. Okay, why do I want that? Well, when the string stretches out, that indicates there's now potential energy stored in it. When you stretch out a rubber band or something, there's potential energy stored in it. How much energy? Well, I'll figure the work done in stretching it out by that much, and that'll be the energy stored. This will tell me the potential energy density. So I would take the force, which is stretching it out by delta L, and multiplying. Force times the change in length will tell me the energy stored in it. So I'll take the force, which is just the tension, multiplied by delta L. And that's basically it. I want the energy density though, so I have to divide by the length dx. And now I just plug that in. I plug in the expression for the change in the length, and I get 1/2 times the tension times dy dx squared. Okay. Now let's see what that's equal to by plugging in the wave function. Dy dx pulls out a factor of k and turns it into sine function, and I got to square it. So I'll get that this is 1/2, and then I have k, t times k squared times a squared sine squared. All right. So we've got the kinetic energy density and the potential energy density. The total energy density is the two added up. However, what I first want to notice is mu times omega squared is actually equal to the tension times k squared. Why is that? Well, it's because tension over mu, isn't that just the square of the speed? But that's the same thing as omega over k. So you can check that mu times omega squared is really equal to the tension times k squared. So the total energy density is these two added together, but they're really equal to each other. So the total energy density is just going to be equal to mu omega squared times a squared times sine squared kx minus omega t. I added them up, but they're equal, so the half disappears. Okay, so that's the total energy density. That's how much energy there is per meter along the string. There are places where the energy is zero. For example, at the top of the peaks, the string isn't stretched, and those pieces aren't moving at that moment. So those places actually have zero energy, but compensated by the fact that at the angled parts, there's stretching and speed, and there's a lot of energy there. So in fact, anywhere it's angled, there's a bunch of energy in those places. So you have these energy pulses that move along as the wave travels. Okay, that's the energy density. It's convenient just to average it out, and if you watched for 5 seconds, the energy would average out to a certain amount, sometimes zero, sometimes more. So I need to take the average of sine squared, and we know how to do that. We learned that the average of a cosine squared or sine squared function is just 1/2. So the time averaged energy density is just found by averaging sine squared gives me 1/2 mu omega squared a squared. Okay, so a couple things to notice. If you double the frequency of the wave, that quadruples the energy. Higher frequency waves have significantly higher energy. Likewise with the amplitude. Big amplitude waves, like if you double the amplitude, that quadruples the amount of energy that's present. This is the energy density, so this is the energy per meter on the string, on the waves on the string. Your textbook will instead write it as the energy per wavelength of the wave. So they will write the average energy um, per wavelength. Which is easy to do. This is the energy per meter. Just multiply it by lambda, and you'll have the energy on a given wavelength of the wave. So that's 1/2 mu times lambda omega squared a squared. Okay. So we have our expression for the energy density, the energy per wavelength. The last thing that I might want to know is what is the average power? In other words, how many joules per second are required to create this wave on the string? A sketch will help us figure out the power. So here's our string. There are waves traveling along the string, carrying energy. And at any little portion of the string of length x, there's a certain amount of energy contained in that portion of it from the waves that are passing through. What I'd like to know is how much energy per second passes through that place. So if I know how much energy there is, I'd like to know the energy per second. In other words, I want to know the energy that's there divided by the time it takes the energy to pass through that place. Well, that's easy. The time that's spent is just x over v, the distance over the rate. So this is going to be the same thing as e over x times the velocity. So that way, if I want to know the power, the energy per second, I take the energy density, the energy per meter, and multiply it by the velocity. So we can finally write down now the average power of the sinusoidal wave. It comes out to be the energy density multiplied by the speed of the wave, which is 1/2 mu times v omega squared a squared. This one will be the most useful equation for us, but along the way we had to prove everything else to get there. It happens all the time that waves cross a boundary from one material into another. Um, and we know that the material is going to change the speed at which the wave travels. An example is someone's talking to you while you're underwater. The waves are going from air into water. What happens to the waves when that happens? Well, we're talking about strings. So let's look at waves on a string. And suppose I have two strings. They're different values of mu. So like one of them is a thick wire and the other one is a thin string. Point is a different mu1 and mu2. The waves travel at a different speed in one material versus the other. So the speed changes. Does that mean the wavelength and the frequency change, or what happens as the waves go across? From experience, with the sound, like listening to someone underwater, the pitch of sound does not change. So we would guess that the frequency of the waves does not change as it crosses a boundary, and that's true. Let's understand why. When these waves go across the boundary, um, the speed's going to change. However, imagine, if you will, that somehow the frequency of the waves is different on both sides. Then wouldn't the string have to break? Because if the frequency doesn't match on both sides, then they're going to go out of step with each other and the string would have to somehow snap, right? So it's easy to argue in that way that for waves on a string, that the frequency must be identical on both sides. F1 must equal F2. Otherwise, the string cannot um, uh, be continuous across the boundary, right? And that's a general property of waves. Even though it goes from one totally different material into another, the frequency doesn't shift. However, the wavelength does. So if the waves slow down, then you start with some long wavelength waves. And when they cross that boundary, now the waves slow down and they're going to pile up on each other. And now you'll have a short wavelength waves. Like so. So the frequency stays the same, but F is equal to V over lambda. So this is V1 over lambda 1 is equal to V2 over lambda 2. So when the speed gets smaller, the wavelength gets correspondingly smaller in order that the frequency stays the same on both sides. Here's an animation of what I mean. On the left, we have fast-moving waves. On the right side, we have slower waves. The n equals 3 means that's the slowing factor. They're moving 3 times slower. Notice that the frequency, though, is the same. The waves bunch together so that the rate at which it vibrates up and down stays the same on both sides. We've got the same frequency, but slower speed and equally smaller wavelength when you change the medium. Example where the speed of the waves change. Ocean waves. The speed at which ocean waves travel depends on the depth of the water. So as the depth is shallower, the speed of the waves slows down. And we saw the kind of effect that has on the wavelength. When the speed slows down, the waves pile up and the wavelength gets smaller. So in the deep ocean, you can have some very long wavelength waves. They pile up on themselves as they approach the shore. We're supposed to understand how a tsunami forms, a huge amplitude wave, by considering this. So first, what physical quantity can you consider to be constant in the motion of the waves as they head toward shallow water? Well, really, I would say there are two. Number one, the frequency, for the reason that we argued. The frequency stays constant as the waves approach. But also, I'm going to assume there's no loss in energy as the wave travels towards the shore as well. So that means that power of the wave is maintained. So although the wave slows down, the energy per second of the wave is going to stay constant. Now, what does that mean? In this picture, all that it illustrates is the shortening of the wavelength when the speed gets smaller. But remember that the power depends on a couple things. If we look back at power, the average power of a wave depends on the speed as well. So if the speed gets smaller, the amplitude must get larger to compensate for it. So what's not shown in this animation is the effect of energy. As the speed is reduced, the amplitude must grow as well. So we should, that's going to explain how the tsunami forms. So the power of the wave is equal to 1/2 mu times v times omega squared a squared. By the way, this equation is easy to remember. It's like 1/2 mv squared. Omega a squared is like the speed squared, the vertical speed, and you multiply it by the velocity of the wave to get the energy per second. Okay, so that's going to explain why the wave gets so big, why the tsunami grows. So that's part B. As the speed decreases, the amplitude increases to maintain the power. I'm assuming no energy is lost as the wave travels along, like from friction or something with the seafloor. So if the wave has amplitude 1.8 meters when its speed is 200 meters per second, what will be its amplitude where the water is only 9 meters deep? Okay, so we're trying to predict the amplitude in shallow water. Call it A2. It starts with amplitude 1 and ends with amplitude 2. So amplitude 2, if I look at the power expression, if energy is conserved, V times A squared is maintained. A sketch might help. Here's deep water, where the speed is very fast, V1, and it slows down, V2. Since the energy is maintained, that means that V1 times A1 squared is equal to V2 times A2 squared. That's conservation of energy. So I can solve for A2. A2 is going to be equal to the square root of V1 over V2 multiplied by A1. So by knowing that the wave amplitude starts at 1.8 meters and knowing how the speed changes as you approach shore, I can solve for the amplitude. So this is equal to, so they give me V1, that's given. I have to write V2 in terms of what's given about the speed of such waves, that it's the square root of g times the depth. So this is the square root of g times the depth of the water at position 2. And that whole thing is under a square root. The number I have is 8.3 meters. You start with a 2-meter wave and it grows up to 8 meters, like basically multiplies by 4 as you approach the shore. That's how the tsunami forms. Question D, explain why the amplitude of the shore could be even greater, but not predicted by your model. Well, we assumed conservation of energy, no energy loss, no slowing of the wave due to friction. In fact, the motion of the water is affected by the seafloor. And so when you get to shallow water, that slows down the wave even more and would create possibly even higher waves. So we did not account for additional slowing due to friction.